Hello, this is chapter 5 or body 5 and it's number systems. So we're going to go through the steps on how to convert from decimal to binary, then from binary to hexadecimal, or even from hexadecimal to binary and then to decimal. So in this, through this chapter, we're going to cover these areas: binary number system and then hexadecimal number uh, system. So under binary number system, we're going to we're going to go through binary, and then we put it in context of IP addresses. So binary numbering system consists of zeros and ones, and they are called bits. Decimal numbering system consists of digits from 0 up to 9. The hosts and servers, host servers, network equipment, using binary addressing to identify each other. So these end devices, what you call the end devices, they use binary addressing to identify each other. So each address is made up of 32 bits divided into 4 sections called octets. So the 32 is it that with the IP address it has to have 4 sections, 1, 2, 3, and then 4. So each section it ranges in decimal from 0 up to 55, 0 up to 55, 0, 0 there. So each section here, this, it has to be equivalent to 8 bits. So 8 times 4, which is a total of 32, which is this 32-bit stream divided into 4 sections, that they are called octets. So each octet consists 8 bits or 1 byte. So the 8 bits here are equivalent to just one byte. So for ease of use by people, the dotted notation is converted to decimal. So the devices, the network devices, for them, they do understand binary addressing, but the human beings or people, for us, we do understand the decimal or the dotted notation or dotted decimal values. So when you look at these two here, we have two topologies. We have one here, and that this the IP address is converted into zeros and ones. Then with this, we have what we call dotted decimal. So for network devices, they use this. And then for human, for us who are to use the decimal, the dotted decimal. So there is a video here. This video will cover the following: positional notation view, powers of 10, 10, which is the decimal or base 10 review. Still, as you can see, decimal base 10 numbering review, binary base 2 numbering review, and then converting IP. This is supposed to be an IP address in binary, then to decimal. So binary position notation, we have it can be any number here, and then we have the radix. Radix, these are just its best. Radix, it's base 10. the decimal. And then we have the positioning number, the positioning number that we have 0, 1, 2, and then 3, and then 3. So 10, if you have 10 power 0, any number to power 0, it's 1. Now here we have a 10, but when it comes to position, it is in number 1. So it's 10. Okay, it's 10 and then in position 1. So it's 10 power 1. That gives you a 10. Here it is a 1. Still it's a 10, but when it comes to the position number, it is in 2. So it will be 10 times 10, which gives us 100. Then still we have the same number, which is 10, but is in position 3. So the position, it's the one that determines the difference. So here it's 10 still times 10, because it is in position number 3, then times 10. So this is 1,000. It's 1,000. We need to note that. So on this other table, we have the position in values, where we have 1,000, 100, 10, and then 1. And then we have decimal number. Now with decimal number here, it can be any number. This. It's not like here in position in value. In position in value, we actually were following the order. In position 0, position 1, position 2, position 3. But decimal number here, it can be any. And for this time, for this case, I'm changing the number. Here we have 1, 2, 3, but I'm going to use 9. Here we can say 9, maybe 3, we have 2, then 1. But we have the positional value. That this 9 here, it is in position as 1,000. So it will be 1, so not 1, it will be 9, then times the position. The position value, which is 9, then times 1,000. Then we have a 3, the position value, it's 100. So it will be 3 by 100. Then we have a 2. It's in between, it's a plus, of course. They have to be bracketed in bracket. Then we have 2 times 10. Then we have 1 times 1, then times position value, which is 1. So here it will be 9,000 plus 300, then plus 2, that is 20, then plus 1. So in total, we're going to have 9, 3, 2, 1. Yes. So binary positional notation, when you look at this in the previous, the radix, it was 10 because we were dealing with 10. Now the radix, it's 2, meaning that we are dealing with base 2. Base 2. So like with it and binary, that an IP address, it has total 32 bits divided in 4 sections, and each section is called octant, and each octant contains 8 bits, or it is equivalent to 1 byte. So whatever that we have here, it is equivalent to 8 bits. So the 8 bits here equivalent to 1 byte. 1 byte. So we have all this. Now we need the position in value. That we have a 2 in position value, position in number, then it's a 0. So it's simply you count 0, 1, 2, 3, 4, 5, 6, then 7. So here, if you to convert, as you can see, we have it's 2 times, sorry, it's 1 times 2 power 7 plus 1 times 2 power 6 plus 1 times 2 power 5 plus 1 times 2 power 4 plus 1 times 2 power 3 plus 1 times 2 power 2 plus 1 times 2 power 1 plus 1 times 2 power 0. So all this they give us, this is 127, this is 64, 32, 16, then 8, 4, 2, and then a 1. Or we can actually have this other one where we have the position in value. So whichever binary number you place under that position value, then it's going to inherit that value. So here we have the position value. As you can see, exactly what we have here, what we got here, it's what we have in the position value. And then you start distributing the bits, whichever bits that you are. For example, here you might put 1, and then here put a 0, 1, 1, 0, 0, 0, 1. So if I'm to convert this, it will be, as you can see, it's a 1 here, the position value. The position value, it's 128. Of course, I'm going to go with this. So it's 128. Here is a 0. I'm going to eliminate it. This is a 32. I need it 32, then plus 16. This is a 0. This is a 0. This is a 0. Here we have a 1. So if I add all these, they will give me total of this plus 32, it's 160. 160 plus this, it's 76. And then 177. You can even prove it. And how are you going to prove it? Just you having this, this what we have there, it's 1, 0, 1, then 1, 0, 0, 0, and then a 1, 1, 2, 3, 4, 5, 6, 7, 8. Give them powers. There is 0, 1. So here we have a 0, there's a 1, then a 2, 3, 4, 5, 6, 7. So 2 power 7 plus 2 power 5 plus 2 power 4, then plus 2 power 0. So this one here, it gives us 128 plus this, it's 32 plus 16 plus 1. So this and this, it gives us 160. 160 plus 16, that is 76 plus 8, it's 177, which is the same as how we have what we have here. Okay, so here it is. I'm not going to actually do anything here, but I'll just request you that you play around with this, because it's the same, only that here it's an IP, a complete IP address. As you can see, it is this. So the second, the third, and then the fourth. So what you're going to do, just to separate, as you can see, that we have this first one here, then let me try to use different colors. have the second one, which is this. We still do the same by using a different color. Then lastly, it's this. So all you need just to come up with a table, your table with radix, with radix where we have 128, then 64, 32, 16, 8, 4, 2, 1. And then you press very well the binary numbers that you given this, distributed them here like this, and then this, this, and then this period, and then you convert them. You'll be able to get back this. So proof, you prove. On this, I'll actually give again an exercise, an optional exercise that you convert this, convert this 200.168.10 and then dot 100. So this time, because here we're given the binary number, you convert it into decimal. But here we have the decimal, please convert it into binary in this format. So decimal to binary convert the conversion. So with this method here, you can actually use. So before I jump to this method here, we have the other popular method or the common method used in converting from any number to binary. For example, if I want to convert 100, so I can use this method by 2. That this is by 2, you get 50, remainder 0. Then 50 by 2, it's 25. Remainder 0. By 2, you get 12. Remainder 1. By 2, you get 6. Remainder 0. By 2, you get 3. Remainder 0. By 2, you get 1. Remainder 1. So our 100, the available binary bits or number, they are here. So it will be 1, 1, then 0, 0, 1, 0, 0. This. So in this space here, always put an X so that you don't write anything there. The moment you have something in this position, it's going to confuse you. So we can actually prove that this and 8 is equivalent to 100 in decimal. How? Give them the powers. So this is 0, 1, 2, 3, 5, then 6. So here, while we have the zeros, I'm not going to convert that because they are zeros. So we have 2 power 6, it is a 64. 2 power 5, it is a 32. Then we have 2 power 2, it is a 4. So let's add 60 plus 30, it's 90. 90 plus 4, 94, plus 2, 96, then plus 4, 100, which means that you are collect. Collect. Now, we're going to use the other method. If you're not actually able, or you're not ready to use this method, you can use the method for actually you be posing questions to yourself. Is this greater than this, or is it less than this? If the condition is true, and then you proceed, or you record and then proceed. Let me show you that you are going to convert the same number. Let's convert the same number to prove whether it's going to give us the same results. See? That if I have 100, because we know the position value, see? Now the position values that it's 128, then 64, 32, 16, 8, 4, 2, then 1. So want to convert 100. So the question is 100 actually, now let's start with the position values. Is 128 less or equal to 100? If the answer is yes, then you record the 1 and you subtract that position in value from, actually it's 100, not 10. So if the answer is yes, we're supposed to subtract 128 from 100. But the answer is no. So we're not going to do any, there is no any action here. So 128, you are going to give it a 0. And then we proceed. Is 64, so it's 64 less or equal to 100? Of course, 64, it is less than 100. The answer is yes. We're going to record the 1 under 64, and then we subtract the 64 from 100, and then we're going to remain with 36. Now the same question, still you go to the next one. Is 32 less or equal to 36? The answer is yes. You subtract 32 from 36, and then you remain with a 4. You go to the next, because here you have to record the 132. You go to the next, 16. Is 16 less or equal to 4? The answer is no. No action there. You go to the next one. Is 8 less or equal to 4? The answer is no. So here, where we have no, if the condition is false, you record 0. So we go to the next one, which is 4. Is 4 less or equal to 4? The answer is yes. You record the 1. You record the 1. And then you subtract a 4 here. You remain with a 0, meaning that these other bits, they are also zeros. So do you have the same answer as this exact answer that we got in the first place using a different method? The answer is yes. So meaning that our method, it is proved, it works the same way as the other one. Huh? So here it is, but the condition used here, it's a single condition where they're saying is which one? So convert decimal, which is this. We're converting 68. So is 68, what's the other saying? Is 68 greater than this? If the answer is, because the question, if the answer is yes, you record a 1. So let's prove this. Is 1, and actually it's supposed to be greater or equal, because there are those scenarios where you'll find that it is equal, like in our previous scenario, that the 4 it was equal to for the other side. So if you just put one condition, greater or less, then it might not give you the exact answer in some scenarios. So is 168 greater than this? Yes, of course, this is greater than this. That's the reason why we have a 1 here. And then if it's yes, subtract this from this. So if you subtract that is 32, yeah, 32, then plus there you get 40. Yeah, actually it's here. So after subtracting this from this, you get a 40. And then you go to this. Is this one here greater than this? The answer is no. So we have a 0. Go to the next. Is 40 greater than this? The answer is yes. Subtract this from this, you remain with 8. Now the question is 8 greater than this? Because this one here, the ones that we have here, these are the position in value, position in value, position in value. These are position in value, position in value. Then what we have this side, it's part of what we're trying to convert, the 168. Okay, so is 8 greater than this? No. So 8, they are actually 16 is, because if we subtract this from this, you get 8. So is 8 greater than 16? The answer is no, because when on this it's a no. Oh, we are considering a 16. Sorry. So is 16 is 8 greater than 16? The answer is no. And then you go to the next one, which is 8. Is 8. Now you see this. The question is 8 greater than this? The answer here would be no, if you go by a single condition. So meaning that you have to have a greater, equal. Is it greater or equal to? The thing is, yes, it is not greater, but it is equal to 8. That's the reason why we have a 1. So when you subtract this from this, you get a 0, and then this side we have the 0. See? So add this and you see whether you will get back this. So 120 plus this, it's 160, and then plus 8, giving us 168. Wow. So here is the same. Convert this into binary. That is what I gave you as assignment. Then hexadecimal numbering system. Hexadecimal numbering system. So we have decimal binary. We have decimal binary, hexadecimal. So in decimal, we have 0 up to 9 because we are dealing with hexadecimal. So in decimal, they have to continue up to 15. But when you count from 0, you'll actually get total of 16. But recording them, we have 0, this, we have to stop at 15. Then when it comes to hexadecimal, we have 0 up to 9. Then from 9, we have A, B, C, D, E, F. F. So all we need to do is just to convert what we have here. To convert what you have here. So if you convert whatever that is here, you will get this. Even when you convert this, you'll get this. But to be on the safe side, you should be able to map this starting from 10. That 10, it's A, B, C, D, E, F. Even if you can't cram this, at least you know that starting from 10, we have A, then B, C, D, E, F. 10, 11, B, C, it's 12, 13 here, D, then 14, C, 15, F, like that. So all we need is just to use the method that we are from actually using, and then you convert whatever that we have here to this. But if I convert 14, I have 14. And these numbers, for you to have the binary number, they have to be 4. They have to total to the total number, the 4 bits. So in 14 here we expect we expect 4 bits. And now we're going to get 4 bits in a more simplest way, that if we have all the bits here, the 4 bits, all of them they are zeros, they will give us a 0. If all bits are ones, they will give us 15, period. So when it comes to 14 here, you need to look for numbers here that we have, and these are actually the position values of these 4. It's 8, then 4, 2, and 1. Some of you will be like, hey, how did you manage to get to the 8, 4, blah, blah. So if I have all bits, they are ones, so I will just give the power 0, 1, 2, then 3. Convert to this. If I 2 power 3, it gives you 8. 2 power 4, 2 power 2, it gives you 4. 2 power 1, it gives you 2. 2 power 0, it gives you 1. And then when you total them, they will give you 15. So for me to be able to convert 14 into binary, I will look for numbers among these that's total to 14. So 8, you can use the other question. Is 8 is not actually, it's a anyway, there are two ways we can compare this by saying, is 8 less or equal to 14? The answer is yes. So if it's yes, you record the 1, subtract this from this, and you will remain with a 6. A 6. So is the next one, is 4 less or equal to 6? The answer is yes. Record 1, subtract this from this, you remain with a 2. You go to the next, is 2 less or equal to 2? The answer is yes. Record the 1 and then subtract this from this, you will get a 0 here. So this is totals to 14. Or you can look for the numbers, just look for the numbers that you can add here, and then they give you 14. So it's 8, this, 12, and then this. For example, let's want to convert 11. So 11, we need 8. We don't need 4. We don't need 4. So this one here is out. We need a 2, totals to 10. Yeah, 2. Then we need even a 1. So it will be 10, then 11. So here it will be 1, here it's a 0, then 1, 1. So please try to go through the steps and you make sure that you get it right. So in hexadecimal, still it works with IPv6. Hexadecimal, the binary works with IPv4 address. Hexadecimal works with the decimal it works with decimal it works with the IPv4, and then hexadecimal it works with 6. So with the unlike IPv4, whereby created at 32 bits, the IPv6 has a total number of 128. And the 128, they have to be grouped in 8 groups, and those 8 groups are here: 1, 2, 3, 4, 5, 6, 7, and then 8. So the total of bits is 128. The section, they are 8, and they are called hextant. Hextant, that is the section. In IPv4, it's an octant. An octant. So here it's hextant. So each hextant here that you're seeing, it's supposed to, within this, it's supposed to have what you call hexadecimal values totaling to 4. So the X here, it has to have 4 hexadecimal, and we have it. Have 1, 2, 3, then 4. In the range from 0 up to FF. Remember this range here, this is how it is. It's 0, then 9 from A up to F, or A, B, C, D, E, F. So that is the range. And here, this range is supposed to be 4. 4, as you can see. The minimum 0, 0, the maximum it's F, F. And then each hexadecimal here, the one that you are seeing is 0 here, it's supposed to have 4 bits. The ones that you are from actually seeing previously here. So now here is a hierarchy that the X, here the X represents 4 hexadecimal values. And those 4 hexadecimal values, they range from 0 up to F, 0 up to F, 0 up to F, 0 up to F. And then this F, it's a must, it has to have 4 binary bits. Still, there can be 0, 0, 0, maximum, it's 1, 1, 1. 1, 1, 1. So if you're to record 1, 1 here, you must have actually increased from 0. Okay, these are the the bits per, as you can see this for this. So on this here, this one here, it represents 16 bits. 16 bits. And then those 16 bits, they are divided into 4 bits, and they are here. So here we have 4 hexadecimal value. Hexadecimal value. And then each hexadecimal value has zeros from 0 up to 1. And these are the bits. So when you total, because each X, the X is equivalent to 16 bits. And the X's, they total to 8. So it will be 8 times the bits, giving us 128. So each each X, it represents what we call an extent. The section, it is extent. Extent. And at the same time, it is equivalent to 2 bytes. The H twice. So that is it. Now I want you to use the knowledge gained in us from this module or the session, and then you work, you go through this example. 168 converted into hexa using 3-step process. So they are here, you can follow them. And then on this other one, it's hexadecimal to decimal, that you have decimal number, which is this, convert it into decimal. Still there are steps, 3 of them. So that is it. So the end of the session. Yeah? Thank you.